let's continue with the experiment. Now, this is the close. Oh, by the way, what you see right now is where this all calculations come from. You have up to this point, you have only seen that kind of two-dimensional, three-dimensional kind of animated virtual lab thing, but the calculations are actually the brain of the whole thing is on this Simulink graph. So what I'm going to do is I'm going to run the system in a closed loop manner and see what's going on. So first of all, let me put everything into perspective. All right, so I'm going to run the system at 21 point, what was that value? I read it from here, 84. Yes, that was the initial value. And I'm going to change this to, let's say, by 2 units. Yeah, 2 units is going to be okay. Or maybe let's change it to 3 units. Or yeah, 2 is okay. Again, this is something like 8. All right. Now we are going to be giving this change to this process. The details are not that much important here. So what I'm going to do here is, there is a controller here. The controller requires us to give the Kc and tau I values. So what you are going to do is, in the very first part of the experiment, you should have come up with some approximate models, or a model at least. So you should have some Kp, tau p, and that time d values at hand. From those values, using Cohen Coon settings, you should come up with some of these values. So for instance, I think in the previous case, I have come up with these values, something like those, I guess, in the first video. Minus 20.8, 162, and 15. Oh, you don't have, MATLAB does not have a comment like this one. So as far as I know, you should write your own Cohen Coon program. I won't be showing you the details of that. It just gives me some values. So these 3 values are required here. Actually, what you do is, let me show you here again on this whiteboard. Let's see. Okay, so what we need is we need those 3 coefficients or parameters, and from the open loop test, you should come up with those values. As I said previously, you may have multiple models, but I'll come to that later. So use one of the models. Actually, I'm going to use the model parameters that is derived for the operating condition around the, what was that value, 21 point something, 21.84. For that one, I have obtained these models, and I obtained the parameters, and I'm not going to show these parameters to you. And from now on, I'm not going to be showing the changes that I'm going to be applying to the parameters, but I'm going to be talking about, okay, let's see what I'm going to show you and what I'm not going to show you. So I feed these parameters. Now the Kc and tau I values are calculated, and MATLAB will do the simulation. Right, let's say that I'm going to run the system again for 600 seconds. Maybe 600 is a bit too much. Let it be 400. All right. So if everything is fine, all right. Now let's animate our model. Okay, initial tank height is about 22 centimeters. This line and this one, these dashed lines show the initial heights. But there's also, as you can see, a red line here. This shows the set point. For the first 20 seconds, set point is equal to 22 centimeters. Now it's going to change. Now, as you can see, it has changed by 2 units, right? Now it's here. Maybe it's better to show it by changing 3 units, that you can see the change more clearly. I think that's a better idea. Let me go back here, and I'm going to change by 3 units so that you can appreciate the change more clearly. What was it, 83 something, well, whatever, that much. It's not very much important. So let me run the whole thing. All right. Again, I'm not first going to show you the online monitoring diagrams. Let's try to get a feeling of what's going on here. So outlet flow rate is equal to 1.99. Now, so you can ask, why does it change during all this time? Because of the disturbance. Now, from this point on, the set point has been increased to that new value, and outlet flow rate is now equal to 0. Why? Because controller, in order to reach the new equilibrium point, to increase height, controller decreases the water flow, the water flow rate here, so that it's going to accumulate water here, and there's going to be more water flowing here, and there's going to be an increase. And as you can see, water is going to be increasing here. And that's very nice. We reached a set point, but unfortunately we have a problem. We overshoot the set point. Water keeps increasing. And the outlet flow rate is still not even equal to 1, which was the initial value. And now this water tank is totally full, as you can see. So it is not something that we desired. As I said, there is overflow right now here, and that should be why this control is not going to be applicable. But there is more to that. And actually, more important thing maybe is we have a pretty much high overshoot. But let's see what's going to happen. By the way, I am just using the Cohen Coon settings. I haven't shown you what the Kc and tau I values are, but I'm using those values. Okay, this water level is decreasing. Why? Because outlet flow rate has increased up to 2. And this is the maximum value. But still this value is higher than this value, the set point. So it is due to the time lag between those two. And now, as you can see, the water level in the first tank is even lower than its initial height. And now it starts to decreasing. Now, even at this outlet flow rate, if you freeze it or if you let this outlet flow rate go further, this is going to continue decreasing, and this is going to decrease even more. So what I would like to say is there is actually a discrepancy between the control action and the water level seen here. Discrepancy is not the correct word, maybe. By the way, this is like kind of live sports game, right? The water is rising and the water is flowing out. But the point is, there is an excessive control action when there is an error, and due to that excessive control action, this part, the first tank, behaves faster, but the effect is transmitted slower to the second tank. And once you see something is wrong with the second tank, the water level is too high, then it is too late because the first tank has already overflown. But as you can see, now after this value, we exceed this value, we see that there's a problem, and now the signal is going to be sent to the outlet flow rate. Well, of course, it's always sent to the outlet flow rate, but the proportional part only at this moment. Now the outlet flow rate starts to increase, but it's too late because this is already totally full. So all this water coming down, so it's going to be increasing. So what we see here is going to be constant fluctuations. Whether these fluctuations go smaller or not, it is difficult to see. So let me now show you this figure to get a better picture. This blue line shows, of course, this first tank. This red line shows the second tank, and here you can see, contrary to the first part of the virtual experiment, what the automatic control is doing. In the first part of the experiment, outlet flow rate was always at constant at 1 with no error. Here is still without error term. Right. When I say error, I'm talking about measurement error or disturbances. I'm not talking about the error between y and y set point. Anyway, now we are under automatic control here. So depending on the difference between those dashed lines and the current value here of the level, this u is changed accordingly. But as you can see, there are very wide fluctuations, and due to the same reason, there are also pretty much wide fluctuations here. Actually, our set point here is supposed to be at 25, but as you can see, we cannot we overshoot the 25 value. Then we continue making oscillations. Whether these oscillations will increase or not, but I think they are decreasing, which should be which actually also says that, or is consistent with the idea that Cohen Coon settings, if you apply them as just they give underdamped responses. So this is a typical underdamped response. Too much underdamped, I may say. Actually, it is close to almost sustained oscillations. If I increase the Kc value a little bit more, then it's going to be sustained oscillations. So this is the moral of the story. It is not a good control. But let this go a couple of minutes further. Because I would like to talk about a couple of more things. One of the things that I should have said, and I missed it, is the sign of Kc. Now, since the sign of Kp is negative, sign of Kc should also be negative. Just refer to your process control lectures. That's again something I should not and I would not go into, because this is out of the scope of the whole thing. But you should be careful about the sign, and I paid attention to that, and I gave a negative Kc value. Otherwise, the manipulate variable would not know whether to close or whether to be opened in the presence of a positive or negative error. But if you don't know about this topic, you should really think about it to understand it more thoroughly. It's not a very straightforward concept. And this negative and positive sign is usually in industry, it is known as direct or inverse action. It is also an important concept here. So when Kc is negative, it is a direct acting controller. So here I'm using Kc a negative value. And as we can see, these cycles tend to get smaller and smaller. Okay, about 400 seconds is going to be, I'm going to stop the simulation, or let me just stop it because there is no need to consider it further. Okay. Now, question is, well, actually that's an awful control, because we cannot reach the set point. It takes a long time. It makes many oscillations. But the question is, how are we going to obtain a good, or how are we going to assess control performance? Although it is obvious that this is awful, let me show this one in a separate figure. This is the response of that 400 seconds of simulation. This is the set point change, right? And these are the readings of from the second tank. Now, we know that this is awful, but how are we going to see, when we see a good one, how are we going to understand that? Hey, do we have some metrics to measure the quality of a control? Yes, we have. And actually, you can see those two metrics here. These are integral square error and integral absolute error. Probably you have seen that, or maybe not, I'm not sure, but you may Google it. Integral square error, integral absolute error. The idea is very simple. For instance, integral absolute error is the area between the set point and the response. Here, a perfect response would have been, since this orange line is the, I think it's orange since I'm colorblind, I'm not sure, but this rectangular line is rectangular curve is I couldn't find the correct wording, is the set point. The ideal perfect response would be the same, would be a line which is superimposed on this set point. In this case, integral absolute error and also square error is going to be equal to 0. Okay, but this is not the case. If this is not the case, what is it? How we find integral absolute error is, now we are not on this orange line, but we are here. So we integrate this area is not the area that we would like. So this is error, this part, and this part is also error, error. Please try to follow. Error, error, and error. The sum of these error values or areas is integral absolute error. And integral square error is very easily, now these error terms are taken square. Now, if these values are much close to 0, or as you can lower them using process control, then it is deemed to be a better controller. But we are also going to use our visual assessment, and I'm going to talk about a couple of more things, but I have connected these so that we can use it for assessment. Okay, so these values are awful. So what I'm going to do is I'm going to change the Kc and tau I values, and this is a very typical response that we obtained from directly applying Cohen Coon settings. So what am I going to do? Let me see this figure again. And this is related with the process control tuning, and it is usually the part which is related with trial and error. And this is how we are going to do in the virtual experiment. Now, this very easily shows that Kc values are too high, and quite possibly tau I values are too low, because it is difficult to distinguish those two, and I'll try to very briefly explain those. And also, I would like to not to show the Kc and tau I values, so it's not going to be a very easy task for me. So what I do is something like this. Without showing you, I hope you do not see this, I'm going to decrease the Kc values by some percent, something like 80, 60, something around that. I don't give the exact values. Actually, exact values will be different, but I know that some of you would just take these values exactly and try that in your experiment without thinking about what's going on. So I want you to think about all these things. So, okay, so this is the old response, let me say. Now I have decreased Kc by something like between 80 to 60%. Of course, with the negative sign also. So I have taken the absolute value of that decrease it. So because, okay, so if the value is, let's say, minus 10, I have changed the value to something between minus 8 and minus 6. Think about it like this. And let me run the system. Okay, let me also change the tau I value. I'm going to multiply it by 2, because increasing tau I means less integral action, decreasing Kc means less proportional action, and also integral action also. And it's difficult, a little bit difficult to distinguish between those two. Let me put it that way. Proportional action is actually the main reason for these oscillations. On the other hand, addition of integral action increases the likeliness to make oscillations. So I don't know how much that means to you, but okay. So for this process, I'm going to run the whole process again. Okay, now you should see that integral absolute error and integral square error values has decreased. Actually, the initial values are, I have noted them here. Initially, this was equal to 359, and this was equal to 252. Now, I'm not going to show the simulation because it's animation is gonna long time, but I'm going to show on the same figure this new controller setting results. Now this is the response of the second tank. And why do we have this response? Also to get a better feeling of what's going on, let me show you the response of the first tank. This is going to be the response of the first tank. As you can see, there is only very little overflow here, except that it's a pretty much good response. And this is actually how the flow, outlet flow has changed. And as you can see on Simulink, you can see all of these at once. So now this is a better control. This is a better trajectory, at least it seems. And oh, by the way, there is something which I would also like to do. I should not forget about this. Now, at this moment, when I do that, it's probably gonna look very strange, but I'm going to write the simulation time. First, I started with a simulation of 400 seconds. I don't need to write seconds. Now I have done another simulation, another 400. I'll explain the reason, and the reason is going to be, the whole thing is going to be very important, as you are going to see at the end. Let me write these values. Okay, so the second tuning with smaller, less control gives a better result. And how do we understand that it's a better result? Because, well, these values, these integral absolute error and integral squared error are smaller. But more important than that, now there are a couple of things we need to consider in responses to understand whether a control is good or not. One of them is overshoot. Overshoot is, well, the ideal control would be the same set point response, but we cannot do that. The overshoot is this ratio, this amount here. So for instance, there is actually an increase of 3 units here, and this one is like 1.5 units. So there is like 50% of overshoot here. Still a high value, but much better than this one. And the second thing that we need to consider is the so-called decay ratio. Decay ratio is that the ratio between the second peak and the first peak. We would like this ratio. There's usually something called 1/4 ratio or 1/4 decay ratio. So according to 1/4 decay ratio, this is like 0.5, and this is 1.5, I guess. Yeah, somewhat. So there is still, the second peak is still a bit high because it's about 1/3 of the first peak. Yet still, this is a better, much better control compared to the first one. And another thing that we need to consider is the settling time concept. I forget where the monitor is. Camera is, I'm sorry. The settling time. Settling time is the time where you can see that the set point has been reached, right? Usually a band is drawn around the set point. If you are within that band and stay there, then you have reached the settling time is the point where you first reached there. Now, unfortunately, within 400 seconds, the system has not seemed to have settled down. So maybe it's impossible to obtain that. So maybe we are going to increase the simulation time and see what's going on, or maybe the control action is not sufficiently good enough yet. All right. So again, without you seeing the control values, I'm going to change them again. Now, if I change the KC value again by the same amount, so I have decreased it. Now take that reference value again, change it to something like 80 to 50%, something like this. Again, I'm not going to give the exact values. So this time tau is constant. I mean, after we have doubled it, the Cohen Coon settings. So here it's going to be easier to see what's going on. Tau is constant. We are only going to change the KC value. And I'm going to run the system this time for 600 seconds to see in the long run what's going to happen, whether we are going to settle down or not. Let's see. These figures are going to be directly drawn by Simulink. Now, as you can see, the second tank has never overflown during this operation, and we do not reach the zero value for the outlet flow for the first tank. So from the first tank. So now I'm going to, on this plot, I'm going to show the response of the second tank, and this is the response. Now let me get rid of that awful one so that we can compare those two. Okay, that's an awful color. I cannot see it clearly, so that's better. So this is going to be our response. Now, what we have done is we have decreased the Kc value. I'm talking about in absolute value, it's always negative. Now, the cost or the price that we pay here in this case, oh, by the way, let's check the values here and the previous values compared to previous values. I think this is 296, 207, slightly maybe worse. But compared to that orange line, as you can see, this seems to be a kind of better control. Why do I call it a better control? First of all, the overshoot is pretty much smaller, right? Compared to this first one. Now the overshoot ratio is about like, if you take the set point here as this is 1 and this is 3, it's about 1/3. I'll come to that overshoot ratio in a minute. Then let's see, the decay ratio is, as you can see, is much smaller than, or about 1/4. So this is pretty good. So let's see what the value here. Can I see? Get rid of this value. So it's about 25.08 compared to set point. This is like 0.3 units. And this is like 1.2, so 0.3 over 1 over, yes, this is almost exactly 1/4 of decay ratio, so that's pretty good. And the settling time seems to be around 300 units. We seem to settle, well, not very fast. So as you can see, if we would like to reach the set point satisfactorily, we are going to need to run the system under closed loop manner for 300 seconds at least. But that's okay. So let me also write it as a quantity here. We have also run the system for 600 seconds. Okay. So it is also a good idea to write Kc tau I while running your process, and these IAE, ISE, of course, that's an awful table, and also maybe some comments here in a table format during your experiments. Please do it, because we go step by step here. Now I'm going to change again one tau I value, Kc value, then it may be a step in the wrong direction. So it's a trial and error. And more than that, it's going to be much more important, as you are going to see in a couple of minutes. So let's see, where am I? What's the tau I value? Okay, let me decrease the tau I value a little bit more. So, okay, I decrease it. I'm sorry, I increase it. I decrease the action of integral action. So I increase the tau I even further. This time I do not do anything to the Kc value. It's going to make me understand what tau I does, more or less. All right, so these values are 207 and 296, the integral absolute error and integral square error. Let's see what's going to happen. Okay, so as you can see, the integral error and integral square error, I think, has got better, or just rewind the video and see what it has done. Let's plot the graph. Okay, this is the result that we obtain, and this seems to be a slightly better control action. Yes, now as you can see, the settling time is about 250 50 units or something like this. It's a pretty good control action, and this spike has been even much more lowered. Actually, let's see what kind of a control action this does in animation to get a better feeling of what's going on. And hopefully we can compare it with the previous always oscillating case. Note that at time 20, during this time there is regulatory control up to 20 because there is a change in initial flow rate. The outlet flow rate is adjusted by itself. Now it's servo control because set point has changed. It increases. Now let's see, there is going to be, this one goes fast. Now this outlet flow rate, note that it hasn't decreased to 0. So it doesn't apply a very harsh function. And okay, there seems to be a slight increase in the first tank. And while this is increasing, the outlet flow rate is also seems to be increasing. It's not stuck at 0.4 value. So it's not stuck at 0.4, and then once it the set point is reached, it again goes back to its initial value. All right, we are close to that value here. Now we reach almost the set point. Outlet flow rate is smaller compared to the initial value, which it should be. Now a perfect control would have been to stop here, but with using PI control, unfortunately, it's pretty much impossible to obtain that. You need also to add derivative control to have that how can I say, to slow down the response kind of thing. But we have a very, as you can see, a very small overshoot, and this tank is not overflown. So even if you find this error is manageable or tolerable, that we have already reached the settling, or we have this process has already settled. You may also say that, but I think we got a better response here. Anyway, if you wait for some little bit more time. You may also think this from this perspective. Note that if we would like to run the system at a higher water level here, the outlet flow rate should be lower compared to the previous case. Why? Because there should be more water in the first tank, and under all the constant conditions, how is it going to be that the first tank is going to have more water? The outlet flow rate should be lower. So now the question is this. It's like solving a question in a dynamic manner, but we don't know the models here. That's what the automatic control is trying to solve. What should be the outlet flow rate such that, or how much should the outlet flow rate should be decreased from 1 liter, so that you are going to increase the water level of the second tank from 22 centimeters to 25 centimeters. This is a kind of what the control is trying to achieve. But during this solving procedure, try to be as close to as 25 centimeters as you can be, is kind of what the control is trying to achieve. So basically at steady state, and we are pretty much close to steady state, the outlet flow rate is going to be smaller than compared to 1 liters per second, due to the reasoning I explained, because there should be more water here, so that there's going to be more water here. So with that outlet flow rate, which is about 0.81, 0.82, whatever, there's going to be a new stable state reached by the second tank, which has a higher water level compared to the first one. Okay, I think that's pretty much sufficient to run the whole thing. So actually for this system, maybe 600 seconds would very little unnecessary, but it is difficult to know beforehand how much time is required. Okay. So, as I said, such a table would be nice. And our last figure, final figure, was this one. Now, this overshoot point. I should also like to mention that. Then I'm going to stop this part, and I'm going to record a part B of that because I think it's already too long. Okay, another heuristic about process control, whether there's the process control trajectory is reasonable or not, is we would like to tune our controller to give a zeta value about 0.4. What do I mean by that? In this most practical sense, let's see what a zeta value 0.4 correspond to. And for that, I'm going to write a transfer function on MATLAB with a zeta value about let's see, is this going to be 0.4 or, all right, actually, I'm not sure about that. So let me see what the zeta value here is. If I have a transfer function such as this one, oh, okay, it's not. And damping is 0.63. Actually, of course, it's not something that I could have calculated it. How is this going to be equal to this number that I write here over 2 over square root of 10? Right, this is, I think, zeta. Yeah, so that 4 should be equal to, if I had done make it 2, yeah, that's pretty okay. So let me make it first 2 and see what it corresponds to, and let me prove that this is the case. So if I put it, yeah, damping is 0.3. So if I give a step change to this underdamped system, this is going to be my response. So this is typically the borderline response that we would like our controller to give us, or our system under closed loop to give us. So this ratio here now, as you can see, is the amplitude is 1.35 and this part is 1. Therefore, there is an overshoot of 0.35%. And this is slightly above, but just on the tolerable limit that we would usually give for our system. So usually what we would like is a slightly lower value. So we can, if I make it to a 2.5, and that's a very awful way of finding the zeta value. If it's 2.5, what's this equal to? Okay, so now zeta is pretty much good, close to 4.4. So if I plot step G, so just to warm your eyes up with what you should expect as a good response, feedback response, this zeta to be equal to 0.4, the step response of a system with zeta to be equal to 0.4 of a second order system is like this one. So actually try to get associated with the overshoot ratio here, how much overshoot we have here. It is like, it's less than 20%. Yeah, it is about 25% of overshoot, right? So the highest peak is about 1.26 and this is 1, therefore we have a 26% of overshoots. So basically a 25% of overshoot is pretty much tolerable, is pretty much okay for a process. And as you can see, the decay ratio here is much smaller to 0.2, and compared to this one, it is much smaller to, the ratio is 2 over 26, much smaller to 1 over 4. So this is a pretty much good control. So if we go back to our figure again, our response, where did it plot? Yeah, it's on the other screen. So of course, this is not exactly second order process. It's probably an even higher order process with time delay, blah, blah, and there is nonlinearity in that. But as I said, this response here, so if you would like to, for instance, determine an overshoot ratio is 25.71. This is 24.83, so it's about 0.9 here. And this value here is, if I recall correctly, it is 4. So it's 9.9 over 4, it is 0.20 to 22% if I have done the calculation correctly, which is pretty good. And the overshoot ratio is okay. Maybe the best that we can do here is to decrease the settling time, but this also seems to be pretty much okay. So you can change these values, play with these values, and see what you can come up with. Now I'm just going to I said I'm going to stop here, but I'm going to one more thing, but this is off the records. I'm not going to put it here because I think I have obtained a pretty good result for these controller settings for this system, which I'm not going to show you. If I increase tau value too excessively, which means I decrease the tau I value too much, which means I decrease the integral action too much. So think about it. If I decrease the tau integral action too much, it means increasing the tau I excessively. It turns into a P-only control, and P-only control gives offset. So let's see if I give a very high. What do I mean by very high? I multiply the tau I value by 4, the current tau I value by 4, and I run the system again. Okay, now I'm going to plot response here. All right. Now here is, if you too much excessively increase the tau I value, which means decreasing the integral action, then this is what you are going to obtain. You may say that, oh, okay, why do we have offset? The reason why we have offset is actually we don't have offset, but we didn't simulate the system for a long enough time. If I simulate the system for 2000 seconds, this time let me show the result. This doesn't gives a very good visual understanding. Yes, now this is better. Now, as you can see, we reached a set point, but it takes a very long time. So what I would like to mention here is about the tuning of PI control parameters. Now, the good thing is the integral action has a very small overshoot. That's great, but then this one, and then increasing to the set point is very small, very slow, I'm sorry. So there's a trade-off, and not very easy to understand trade-off between Kc and tau I values from P-only control and integral control. That's why I said integral control contributes to oscillations, but actually the oscillations are, if you have a higher order system, is due to the P-only control, but integral part increases or may just move itself from oscillations, and that seems to be a good thing, but it is not. So it in this case, it takes a long time to reach the set point. Okay, I think that's enough. I'm going to continue with tuning, but little is left in the second part of the lecture.